Hello everyone, my name is Mark Shipman, founder of Quanticarlo, and today I'm going to be giving a demonstration on prompt optimization using chain of thought. So the data set we're going to use comes from Kaggle. They have a data set here and the challenge is LLM classification fine-tuning. Fine-tuning is often a technique that's used to train foundational models, pre-trained models, so that they can perform certain predictive tasks better. In this case, it's classification. So let's take a look at the data. Might help understand the task a little better. So in this data, we have, in this particular set, you have in the training data, there's two models. For each row, there's two models. And in this case, you see GPT-411, GPT-40613, and then there's a prompt, and then there's two responses. So they have one prompt that's given to each of these models and then a different response for each model. And the task is to judge which one is better. So this is labeled data. So a judge has picked one, and you can see here, winner model A, winner model B. A judge has labeled one of these two responses better. So the idea is to train a model using fine-tuning to be able to predict the result of the judge, of the human labeled examples. So what we're going to do is we're going to solve this task using chain of thought. So chain of thought is a technique from Agentic Reasoning where you prompt a model multiple times going back and forth in order to get a better answer. And it can basically be used as a substitute for fine-tuning. So when you have several different LLMs with different prompts interacting with each other, we call those agents, and we call that agent orchestration or agentic orchestration. And so that is the chain of thought, is you have an answer from a model and then you build it up by the model essentially talking to itself. So in this simplified example, what we're going to do is we're going to do prompt optimization. We're just going to try and optimize one prompt, which is an example of agentic reasoning. So one reason that chain of thought is actually it might be a good choice better than fine-tuning is that orchestration is simpler. It's easier to deploy. So for example, fine-tuning, if you have several different tasks, you may have to fine-tune a few different models. With prompt optimization using chain of thought, you really only have to orchestrate prompts. So you can use the same model. It's the same model. You didn't have to fine-tune it, and it's deployed. And then you can have your orchestration is by orchestrating the model talking to itself using different prompts. And this has been shown to solve certain tasks as well as fine-tuning. In certain cases, it's actually better than fine-tuning. ChatGPT famously beat 80% of first-year law students on the LSAT, more than 80%. And the LSAT is a task that's a little bit more complicated. It's a reasoning task. It's more like a general intelligence task. So it's actually more complicated than fine-tuning. It requires sometimes some reasoning, and that's what they're showing now through agentic reasoning. You can actually get these models to do more complex things. So sometimes it's actually better than fine-tuning. Agentic reasoning can also be performed without labeled data, which is kind of amazing. So you could actually have the model actually ask questions to itself, much like humans do, and then reason over multiple iterations about why something may or may not be true, and then provide an output just based upon its reasoning process. There you're relying on the reasoning process. So sometimes to get better accuracy, of course, labeled data is better. So this will make a little more sense when I go through an example. So let me go through an example here that we're going to go over here in the demo. So the first step is we'll have a model propose prompts. And then in a combination with the prompts and the training data, and remember the training data is a prompt and two responses. So the first prompt is going to ask the second model to evaluate the responses. So there's one model talking to another model, really talking to itself. So it's asking itself to evaluate the two responses based upon the original prompt in the data. That second model is then going to propose an argument about which response is better. The third model is going to evaluate those arguments. So keep in mind that it's really the same model, but it's being prompted in different ways. That third model will then produce a score, which basically says which model is better, and then that score will be used in the Bayesian optimization process to come up with better prompts to go through the cycle again. And through this process, that first set of prompts gets better and better and better. And this is the prompt optimization process. And so this conceptually can be extended to just generic text optimization. So in this example, we're using multiprocessing to orchestrate. So that means that each process is making a separate call to the GPU. So each one has its own GPU. So there's 4 GPUs on this machine. And so there's going to be 4 processes, each making a separate call to a GPU, to an LLM. And this is how we will scale. So if it takes 3 or 4 seconds per call, then you can run it 30 times, 100 times, and then you get your scale that way. So if we look at each process, what it's doing, it's going to instantiate 2 different versions of a model. The first one is high temp. So the original prompts are going to be proposed with high temp so that we get a large space of possible prompts, and there's different ways to do that. But it's going to be evaluated and scored using low temp so that it's consistent. So let's look at some of the original prompts here that were in the first batch. So the original prompt, the evaluating prompt, not the one that does the evaluation, but the one that asks the second model to evaluate. Compare the coherence and relevance of the 2 provided responses to the original prompt, analyzing their ability to address the question or topic. Identify which response is more effective, conveying a clear and concise answer, and end your evaluation with the recommendation of which response is superior, labeling it as the better response. Here's a second prompt that was proposed by the first model. Compare the 2 responses and select the one that best addresses the question with the most clarity and accuracy. Analyze the content, tone, and overall quality of both responses. So what you notice here is that each of these prompts is using a different criteria, slightly different grading criteria. And so that's why you will get slightly different answers in the arguments being made. And then in the final stage, you actually get an evaluation of those arguments that are being made. And so then that's how you get different scores and different answers and different qualities of responses. So let's look at the arguments that are being made. So as a result of that first prompt, the argument, response 1 provides a comprehensive list of strategies for creating a test set for a very rare category, including synthetic data generation, oversampling, transfer learning, and using data from related domains. So let's look at the second argument made from the second prompt. This response provides a more comprehensive and detailed list of strategies for creating a test set for a rare category, including the use of synthetic data, oversampling, transfer learning, class, balanced data sets, and online data. So you see they've made different arguments, and they're going to have different results, and then they're going to have different performance. But as you go through the space, eventually you're going to understand how to optimize that original prompt so that it eventually gets to a point to where the results are matching the results of the data set. So again, this can be extended to all kinds of ideas. You could have a whole population of responses, and that population can have different personas. They can have different reasons for giving those answers, and then in that way you also can get a probability and a confidence interval for each answer and each response. So if we look here, just here at the performance, so I called them batches. Each pass, each part of the loop was a batch, but each device, so there was 4 at a time, so there's a device number. So there's 5 batches, 4 devices, and for each one of those is a different prompt, and you can see the accuracy for each one of those. And so what happens is, as you go through these iterations, these accuracies will get better and better and better, and that's the role that Quanti Carlo plays. Is that Bayesian optimization, Quanti Carlo is able to improve the speed of that by over 80% so that you can scale this to hundreds, thousands of iterations much more quickly. Thank you for watching. I'm Mark Shipman, founder of Quanti Carlo, and this has been my presentation for using chain of thought for prompt optimization.